Okay, that part works. Let's see if we can get the other part to work. Okay. So we're good. Okay.
I did most of it. We have like one hour where you find the problems that legislators on the syllabus, right?
Yeah, on the syllabus.
Also,
What?
when is it due?
It's due Wednesday, I think, before class.
Thank you, because I was like trying to find it, and I was like, I'm under the 50 days.
Yeah, I think in one of the emails he sent, he just said that whatever the homework is for that, like, on the syllabus, this is for that week. It just is due by like the following Wednesday after like that week. And it's due like on like one note or whatever.
Alright, I was just like looking for, I was like, I'm sure do soon, but yeah, I don't know. Thank you.
So were you able to access the videos from Zoom at all?
Yes.
You want to try to?
Yeah.
You were able to see them? Okay, okay. Yeah, I may, if, knock on wood, right? I mean, I may try to actually, since they only last on 30 minutes, 30 days, sorry. I may try to, set up a YouTube channel so that you can have an archive. So. My daughter's helping me out. Helping see how it works. She's pretty good at it. And I'll try to continue to post those also. Yes. Okay, let's do a little sound check. Can everyone hear me on the other end?
Yes.
Great, we can hear you really well, so. Good, I'm just gonna turn off the lights. Okay, I hope everyone had a good weekend. All right, so I'm going to start back in on systems of equations and AX equals B. So let me kind of back up a little bit and then I'll review. So let's start back on systems of equations. So, you have an m by n system. So m equations and n unknowns. And so it looks something like this. You have a11 x1 plus a12 x2 plus a1 n xn is equal to b1. Okay, so that's the first equation. And then you have a21 x1 plus a22 x2 plus a2n xn is equal to b2. And then you have m of these. So this is am1 x1, finally amn xn is equal to bn. Okay, so here I have m equations and n unknowns. Now we don't want to keep on writing these equations out all the time, so there's a more compact way to sort of express these equations. So the first thing is we can sort of set up a system, and we're going to label this by ax equals b. Okay? And what is A? The matrix A will be the matrix involving the coefficients involving the A's. Okay. And so what I'm going to do is I'm going to look at the columns of A. So let me label the columns of A as follows. V1, V2, up to V sub n. Okay, so these are vectors which are in the columns of A. So when I write A times X, then what I'm doing is I'm actually writing a linear combination of the columns. So that was the definition of A times X. So AX is equal to x1 v1 plus x2 times the second column plus xn times the last column. Okay, remember this was the definition. All right. And now I'll just combine this. So what does AX equals B mean? And this happens if and only if x1 v1 plus xn vn is equal to the vector B. All right. So now we can actually just put all this together in a theorem. And so let me write out that theorem. So theorem. So the matrix equation, AX equals B, has the same solution set as star. Okay, so let me go back up to star. So star is this system of equations. Okay. Comma. And is equivalent to this system up here, x1 v1 plus x2 v2 plus xn vn is equal to b is equal to b. Okay? And is equivalent to solving this system using Gaussian elimination. Okay? All right, so all these things are the same, right? So if I want to solve a system of equations, we knew we can actually put it in this matrix form down here. And now what we actually do is we have a connection between solving the system of equations and looking at spanning of certain vectors. Okay, so now let me say the following. So the following statements are equivalent. Okay. So statement number 1, AX equals B has a solution. Okay, so I'm just looking at this system of equations and I want to actually know whether the system has a solution or not. 2, B is in the span of, okay, now you fill in the blank. So AX equals B has a solution if and only if B is in the span of what? Just look at the theorem. So what does it have to be in the span of?
Okay. The
Of what?
vectors x1, v1 plus x2, v2, et cetera, et cetera.
So I want to just parse this out. What are the vectors? You're almost right, but what are the vectors? Are they the x's or are they the v's?
They're the X's.
The x's. The x's are numbers, right?
Me.
V's, right? So B is in the span of V1, V2, up to Vn. So these are the columns of A. Okay? So we have a solution if and only if the vector B is in the span of the columns of A. Okay? 3. B is a linear combination of what vectors?
V1 and V2.
V1, good, V2, up to Vn. Okay? So all these three things say the same thing. We have a solution for the system of equations, or B is in the span of the columns of A, or B is a linear combination of the columns of A. Okay, any questions on this? All right. So let's do some actual exercises. Let's do some examples. Okay, so first example. So let B be the vector 8, 2, 3. Okay? Where the matrix A is equal to 4, 3, 5, 0, 1, minus 1, and 1, 2, 0. Okay, so this is the given. So does AX equals B have a solution? Okay, so that's the first question. I'll ask the second question after we solve this. Okay, so to determine whether this has a solution or not, what should we do?
Split it up into one.
Reduce it.
Yeah, so we want to form, you know, our system of equations, right? So 4, 3, 5, 0, 1, minus 1, 1, 2, 0. So that's the A part. The B part's 8, 2, 3. Good. Let me see if I can fix that a little bit here. Oops. Erasing here, and then we'll fix that. So let's see if that we can do that. Let's look at it. Okay, so we're going to try to solve this system of equations. We're going to use Gaussian elimination to actually do this. All right, so let's do that. Okay, so I have a 4 up here, so I've already got a 0 down here. So if I want, I could just multiply the third row by minus 4, add it to the first row. So I could do row 1 plus minus 4 times row 3. So I don't have to work with fractions, and I can put in the third row. Okay, so I can just do that. All right, so let's do that. So it's 4, 3, 5, 8, 0, 1, minus 1, 2. What do I get? I get 0. What's the next one? 3 minus 8 is what?
-5.
Negative 5, good. What's the next one?
A 5.
5, very good. Next one?
-4.
Negative 4, very good. Okay? All right. And now let's just reduce one more time and see what we get. And so what I want to do, I want to multiply the second row by 5. And then I want to add it to the third row and then put it in the third row. Okay, so we have 4, 3, 5, 8, 0, 1, minus 1, 2. And I have a 0, I have a 0, I have a 0. And then what's the last thing?
-14.
Let's see, I think it's a 10 plus minus 4, right?
Oh, 6.
6. Okay. So what's the conclusion here? So I have like 0 times x3 is equal to 6. So what can I say now? Good. So there's no solution. Okay, so there's no solution to this system of equations. Okay, so that's question number 1. Okay, so the next question is B here a linear combination of 4, 0, 1, comma, 3, 1, 2, comma, 5, minus 1, 0. So is B a linear combination of these vectors?
No.
No. Okay. And so the answer is no, because AX equals B does not have a solution. Okay, any questions on this? So if we want to see whether vector is a linear combination of the other vectors, we just set up a system of equations, and then we figure out whether there's a solution or not. So I think I have an example where we do that. Yeah. Sort of. Okay, so I have another example. All right. So here's, let me call this example 2. Okay, so we'll go over this carefully. So 2. So do the columns of the vector A, which is equal to 2, 0, minus 3, 4, 1, minus 5, and minus 6, 3, 7. So the columns of this matrix span R3. Okay. So what we have to do is we have to think about this problem, and we sort of have to figure out, you know, what the problem is really asking for. Okay. So what does it mean to span R3? Well, it means that I can get any vector in R3 as a linear combination of what? The columns of A, right? So another way to say it is, does, maybe it's better this way. So the question is every vector B, let me call it B1, B2, and B3 in R3, a linear combination of the columns of A. Okay, so this is equivalent to actually spanning R3. I want to be able to express any vector in R3 as a linear combination of the columns of A. Okay, this is equivalent statement. So to answer that question, what I do is I set up, what do? I set up I already put it up there. So what should I put on the left-hand side here?
A.
A, good. 2, 4, minus 6, 0, 1, 3, minus 3, minus 5, 7. And then here I'll just put B1, B2, and B3. So to see whether B is a linear combination of the columns of A, I just have to try to solve this system of equations. Okay? All right. Okay, so I don't know what B1, B2, and B3 are, but what I could do is I could just use primes or something like that to sort of indicate that, or else I can actually, write things out. But let's just do this anyway. All right, so first of all, we don't have to do anything to the second row. So the third row here, what I'm going to do is I'm going to multiply the first by 3 and the second by 2. So I'm going to take 3 times row 1 plus 2 times row 3. And I'm going to insert that into row 3. Okay, so I don't have to work with fractions. That's the reason why. So 2, 4, minus 6, B1, 0, 1, 3, B2, that stays the same. And so what do we get? We get 0. What's the next one over here?
2.
2, very good. Next one? Minus
-4.
Minus 4, right? Good. And then the next one is, I'll just call this, I'll call it B3 prime, okay? I mean, I could actually work it out, but it's just some number, right? It doesn't matter. Okay, So we're going to do one more elimination. So we're going to make that 2. And then we're going to just do the same deal. Okay, so I get 0, and I get a 0 here. And then what do I get here? I get -6 minus 4 is -10, right? And I'll just call this B3 double prime. All right, it's, again, some number. All right. Now, I think this is in your homework. I actually was helping a student today on this. So what do you notice about this matrix on the left-hand side? Yeah,
In echelon form.
right. But what do you notice about this here? These are the pivots, right? And so there's a pivot in every single column. So like by the homework problem, we know there's a unique solution. Right? So because we have all the pivots in the system of equations, we have a unique solution. So since we have all the pivots in this 3x3 system, there exists a unique solution. I mean, you can kind of see already that it has to have a solution because, you know, we have like 10x3 is equal to B3 double prime. So I can solve for x3. And then I can go to the next equation. I can solve for x2. And then I can just back substitute up to the third equation and solve for x1 also. So we definitely know, because we have non-zero pivots, that we actually have a solution to the system of equations. All right, so what's the answer to the question? Is every vector a linear combination of the columns of A? Yes. So hence, the columns of A span R3. Okay? All right, any questions on this? The ideas? Okay, good. All right, so now we can actually move on. So we're going to move on to looking at specific types of systems of equations. So let me start off by saying I want to look at solutions of homogeneous and non-homogeneous systems of equations. Okay, so this is the next topic. All right, so let me say what a homogeneous system is. So a homogeneous system is a system where I have AX equals the zero vector. So this is homogeneous. Okay. So a non-homogeneous system is when I have AX equals B and B is not equal to 0. So I have AX equals B and B is not equal to the 0 vector, and this is non-homogeneous. Yeah. So at the end, what I'm going to do is I'm going to show you that even though these may look different, I mean, B could be anything you want, which is non-zero, it turns out there's a connection between the non-homogeneous system and the homogeneous system of equations. A very tight connection. Okay, so I want to mention something else. So if I take what's called the null space of A, this is going to be the set of all solutions. So let's see, this has to be in, so m by n, Rn, such that Ax equals 0. So these are solutions to the homogeneous system. And this is called the null space. All right, so sometimes I'll refer to the solutions to the homogeneous system as the null space. All right, so let's calculate an example. We'll do a very simple example at first. And then from this example, we'll actually be able to see the relationship between the homogeneous and non-homogeneous. All right, so let's start with the matrix. I'm going to start with a nice, easy one, 2 by 2 system. So 1, 2, 2, 4. Okay, what could be nicer? So what we want to do first is we want to look at Ax equals 0. Okay, so let's look at the homogeneous system and solve it. All right, so how do we do that? Well, we just do it the way that we always do. 1, 2, 0, 2, 4, and 0. Okay, everybody okay with that so far? All right, so let's solve. Okay, so I'm going to multiply the first row by -2. We're going to add it to the second row and then put the result in the second row. So I get 1, 2, 0, and that gets 0, 0, 0. Aha. Okay. So let's see, this is a pivot up here. Are there any free variables? Okay. So this variable is x1 and this variable is x2. So which variable is free? x2. So x2 is a free variable. Let's call this t. Okay. And then we just back substitute to get the solution. So we have x1 plus 2x2 equals 0. So that's x1 plus 2 times t is actually equal to 0. x1 is equal to minus 2t. Okay. All right. So then the solution is x1, x2. This is going to be what? This is going to be minus 2t, and this is going to be t, and this is going to be t times what? Minus 2 and a 1. Okay, so we just get a line which goes to the origin. Everybody okay with that? Yes? Okay, so another way to say this is that the null space of A is the span of the vector -2, 1. Okay, this is another way to say this. You just take this vector and you look at its span, which is just multiples of this vector, and that's the null space. Okay, so it's just a different language, a different way to express things. Okay. Now, what we're going to do is we're going to take the non-homogeneous equations for this system, and we're going to solve them. Okay, so this one was the homogeneous system. And now let's solve the non-homogeneous system. Okay, so we have AX equals B, and I'm going to do the non-homogeneous. Okay? All right, so let's solve this. Okay, so I'm going to put the equations in again. So 1, 2, 2, 4, B1, and B2. Okay, so this is AX equals B, and we want to actually solve the non-homogeneous system. Okay, so we just do this the same way. Multiply first row by -2, add it to the second row, put in the second row. So 1, 2, 1, 0, 0, and what's here? It's -2B1 plus B2. Okay. So when does this have a solution? Does
When
it
the
all-
equation 0 equals negative 2b1 plus b2 is true.
Right. So this is consistent if and only if -2b1 plus b2 is equal to 0. Okay? So it has a solution if and only if this is true. All right, so let's suppose it is true. So now suppose that -2b1 plus b2 is equal to 0. Okay? All right, so then if I go back to my system over here, I get 1, 2, b1, 0, 0, 0. Okay, that looks pretty good. And now I can just solve my system of equations again, right? So I have x1 here and x2. What's my free variable?
x2.
So x2 equals t is free. And now I just back substitute. Okay, so there's nothing to do in the bottom equation. But then I have x1 plus 2x2 is equal to b1. Okay? So that means x1 plus 2 times t is equal to b1. That means x1 is equal to b1 minus 2t. Okay, so I have x1 and x2. Okay? And now let's write out the solution for the non-homogeneous system. So the solution will be x1, x2. So what do we get? We get b1 minus 2t. Okay? And I have a t here. And I could separate this out as b1 and 0 plus t times minus 2, 1. Okay. So anything, do you notice anything about this? I mean, is there something that looks familiar in this? I mean, let's compare it to the homogeneous system. So here's the homogeneous system up here. Here's the non-homogeneous system. What do you observe?
The non-homogeneous is this same plus a coefficient?
Yes. So a piece of the non-homogeneous system involves the homogeneous system. Okay, so let me just kind of, I don't know, let's see, I think it's a red and black day, don't you think? All right. Oh, the school spirit area. All right. So this piece over here is the homogeneous solutions. Okay, so the non-homogeneous system of equations involves the homogeneous solutions. And then this particular B is actually a particular solution. So let me make that, let's change colors. I don't know, do you like green? Let's try green. All right, so, so this one here, this one is a particular solution. Of AX equals B. Okay, and so I've gotten a solution where I take a particular solution for the non-homogeneous and I add all these homogeneous solutions to them. And that gives me all solutions. And miraculously, that's true in general. So let me actually write this out a little bit more carefully. Let's go back to the black here. So our solution here, X, is a particular solution plus X of H, where X of P is a particular solution and the homogeneous part is in the null space of A. Okay, so we just take all things in the null space and then we add a particular solution, we get all solutions that way. Okay, so now what I'll do is I'll summarize this in a theorem. Okay, so here is, if you want to call it the executive summary, you can. So let A, B, and M by N system of equations, or M by N matrix. That's a better way to say this. So M rows, N columns. And now we want to consider the system of equations AX equals B. Okay? So let X of P be a particular solution of AX equals B. All right? Then the set of solutions for AX equals B are of the form X equals this particular solution plus X of H, where we look at every single homogeneous solution. So we're actually in the null space of A. Okay, so this is the set of homogeneous solutions. All right, so how many people have taken differential equations before? Okay, does this look familiar to you? I mean, you have a differential equation, and then you look at the homogeneous differential equation and the non-homogeneous one, and you could express the solutions for the non-homogeneous ones as a particular solution plus the homogeneous one. So if you've taken like differential equations, you might have seen a theorem just like this, or like differential equations. Okay, so let's see. Let me first justify why this is true, and then I'll draw you a picture. Actually, let me draw the picture first. Okay, so I changed my mind. All right, so let me draw the picture first. Okay, so here's the actual picture of the way you should think about things. All right. Okay, so let me put in the axes first. So let's say I'm in 3 space like this. Okay, so I don't know if you want to do X, Y, and Z here. Okay, so that's 3-dimensional space. Okay, so when I look at the null space, it turns out to be a linear space which actually goes through the origin. So let me depict the null space by using some green, okay? So the null space here will look like a plane like this, which actually goes through the origin, because 0 is the solution for every homogeneous system. So this part is the null space over here. Okay, pictorially. It could be a plane, it could be a line, but it has to go through the origin. Now, in order to get so this gives me the homogeneous system down here, the stuff in the green. Now, to get a particular solution, or get all the solutions, I have to take a particular solution and I have to translate this plane up. Okay? So let me do that. Okay, so let's use black again. So what I can do is I could take a particular solution, let's call this x of p, right? And to get all the solutions, I just translate the null space up to the tip of x of p. So let's do that here. Let's change that into red. And we get a plane which is parallel to this, but now it's kind of stuck up here. Okay? So that point is actually on the plane. And this gives me all the solutions. So this will give me the solutions of AX equals B. Okay? So geometrically, what's happening is that your homogeneous solutions sort of are some space which kind of goes through the origin, and then your solutions for the non-homogeneous one, you take a particular solution, you just translate it up. Okay? Any questions on this? All right. Yeah, linear algebra is very nice. Okay, so so now it won't take me very long, but let me just justify this so it's not like some voodoo mathematics. Okay, so let me show you why this is true. It's not hard. Okay, so you want to call this a proof, you can call it a proof if you want, but I'll just call it a justification. All right. Okay, so first thing is if you take anything of the form x particular solution plus something in the kernel, or the null space of A, then we know that this is a solution, right? Because if I take A times X, this is A times the particular solution plus, ooh, okay, I'm okay now. Plus, let me move it up a little bit. The homogeneous solution. And you could show that you can sort of bring these out individually. Now I have a particular solution up here, so that means that this is going to be B. And then this is the homogeneous solution, so this is going to be 0. So that means that if I take A times X, I get B, when I have a particular solution plus a homogeneous solution. So this actually gives me a solution. Anything of this form. Okay? All right. So now I want to say, suppose I do have a solution for AX equals B. I want to be able to write it as a particular solution plus the homogeneous one. Okay? So suppose that we'll just call it X is a solution of AX equals B. Okay? Let me call it X prime, just so it doesn't get confused with the X that we have in there. Okay. So what I want to do is I want to consider X prime minus this particular solution. Okay? Then if I take A times X prime minus the particular solution, so I do the same trick as what I did over here. This is A times X prime minus A times X particular solution. Both are solutions of AX equals B. So I get B minus B, which is 0. Okay? So what does that say about the difference X prime minus XP? What does that say about it? It's a solution of what? Anyone? Anyone from the other end? What have I just shown here? I've shown that A times something is equal to 0. So that something is a solution of what?
A null space?
Yeah, that's going to be in the null space, right? So that means that X prime minus XP is a solution of AX equals 0. So that means that X prime minus XP prime is equal to XH, where XH is in the null space of A. Okay, it has to be a solution for the homogeneous system. And now that means that X prime is XP plus XH. Okay? So what I've done is I've taken a solution for the non-homogeneous system, and I've expressed it as the particular solution plus something in the null space. All right, so I'm done. So it's not very hard. I mean, it's just using the definitions. But the result is nice. The result says that, you know, to know the arbitrary solution for a system of equations, it involves basically just one solution plus homogeneous solutions. And that one solution can be any solution you want. Okay, let me stop this part of this discussion now. Are there any questions on this?
I have a question about like the null space in general.
Yeah.
So what if, is it ever a possibility that the null space and the solutions of AX equals B are like at an angle in terms of the plane?
No, they're always parallel.
Okay.
This is what this theorem says. They're always parallel to one another. Yeah. No, this is a very strong theorem in that respect. It's a good question. There's not much that can really happen. That's what this theorem is saying. Okay, other questions?
Yeah, I actually have a question.
Go ahead.
So is this null space stuff just another way of naming the span of things, basically?
Yeah, so what you do is you look at the solution, and this is a good question. So what we'll do later is we'll actually be able to find what's called a basis for the null space. And the null space will be a span of those vectors in the basis. So what you're asking for is something we're going to do later on. Okay, so we'll actually go to find the null space as a span of vectors.
Okay, thank you.
That makes sense? I hope so.
Yeah.
Okay. Very good question. Other questions? Okay, so next time what we'll do is we'll actually do more examples of this, a little bit more sophisticated examples of finding systems of equations. We'll actually express the general system, general solution as a particular solution plus something in the null space again, maybe for a 3x3 system. And then towards the end of the week, and maybe we'll even start on this next time, we'll look at applications involving electrical networks and then balancing chemical equations. Okay, great. Okay, that's it. We'll see you
Thank
on
you.
Wednesday.
Have a good day. Thank you.
All right, thanks, you too.
Thank you.
Okay, see you. All right. Let's see.